because of even or odd parity. Okay. So let's work on the right hand side. So we're dealing with this part. So for x greater than 0. Now here's our general solution. Now if x is positive on the right hand side there, let's assume wait a minute, alpha and beta are positive, right? Is that? Let's see. Let's assume our energy is positive, so alpha be positive. Now we're assuming E is less than V, right? For this part of the problem. So that makes beta positive, right? So alpha and beta are positive. Now if beta is positive and x is positive, as x goes to infinity, as you go out this way to infinity, this value here is going to blow up. It will go to infinity, right? Because these are both positive, and x goes to plus infinity. The exponential will go plus infinity as well. All right. So therefore, to kill that, that's not physical. We don't want infinities in physics. I can tell. You wait till we get quantum field theory. You'll appreciate the humour in what I've just said about we don't want infinities in physics. I'm jumping ahead a couple of courses. Right. Okay, so we don't want this. We don't want this to blow up, so we make D 0. Right? That's we can't have D being non-zero because we get these infinities. U would go off to infinity. Right? So e to the bx here would go to infinity as x goes to infinity. So make D 0. Reject that. All right. So we're left with this. Now, for equation 1 that we've done before, remember U takes the form of A sine plus B cos, that sort of form, right? Now let's deal with a case of even parity. Alright, so we're getting all these sub-cases now. So one case is when E is less than V naught. Another case is even parity. You can do it for odd parities. So we're getting all these sub-cases. Alright, now for even parity, you had A sine plus B cos. So you want the sine part to disappear because sine is an odd function. Sine of minus x is minus sine of x. So we're talking even parity, so let's get rid of the sine. So you've got A sine plus B cos. So make A 0. So that leaves you with B cos. That's an even function. That's what you want because we're now dealing with even solutions, right, to U. So now we've got, so we're left now with U is B cos, well, alpha x, right, in this region, so between naught and A. So we're talking about from here to here, right? And in that region, the solution U, your wave function, is of the form B cos alpha x, right? Now, we've also got, this is for x greater than A, right? So in this region here, we have U is of the form, where is it here? B cos alpha x, okay? Sorry, here. Sorry, here, this one. Okay, now, so we have a solution here of this form, valid in this region. Okay, and we have another solution here that's valid in this region. Now remember, we've done this now. This is now the third time we've been doing this. You impose your restrictions, your conditions on your wave function. Single valued, normalizable, and continuity in the wave function itself, and continuity or smoothness in the first derivative of the wave function. Okay, those conditions. All right. Well, let's do continuity So the value of the wave function here at x equals a must equal the value of the second solution in this region. Those two have to be equal at x equals a. So you don't get sudden jumps, right? The values meet. They're the same value at that boundary at x equals a. Therefore, let's see. These two solutions here, they have to equal each other when x equals a, right? So therefore you get b cos alpha a, there it is, equals this, c e to the minus b a, right? So that's where the two wave functions are equal. Now let's take the first differential, so du by dx, and those two gradients have to be equal. So it's not enough just that the two values, the two wave functions are equal. I mean, they might be like this. They have different gradients, but that means you get a sudden jerk in the gradient. You don't want that. That's not very physical either. So you want the gradients to sort of be the same, right? So okay, so differentiate both of these. So you'll get minus b sine alpha x and an alpha as well. So that's where this comes from. And differentiate this with respect to x, and you'll get minus beta c whatever. Okay. Do that for homework. All right. Now take this equation here and divide by this one. So the b's cancel, the c's cancel, the exponentials disappear, and you end up with getting just tangent tan of alpha a is equal to b over a, right? B over a. So call that equation 3. So so tangent of alpha a equals beta over alpha, right? Now so we've deduced that much. Okay. Now if you take a different subcase when the parity is now odd, because we did here parity for even parity. So if you do it for odd parity, what's your wave function that has odd parity? Now u is the general form, remember, a sine plus b cos. Now you want now you're doing the odd parity case, so you want u to be an odd function. So that means you have to kill off the even function, and that's the cos, because cos is an even function. So you want the b to be 0. Okay, so that leaves you with a sine. Yeah, a sine something. Right, so you do a similar analysis to here, and I'll ask you to do this for homework, asking you, especially this part here, asking you to do quite a bit of homework. It's getting tougher, right? It's it's a senior level course. So do a similar analysis, and you'll end up with something equivalent to this. This is equation 3, and you'll end up with equation 4 for the odd parity case, and it'll be cotangent, cot alpha a equals minus beta over alpha. Right? Just do the similar analysis to here. Impose these two conditions, and you'll get this. Right? Okay. So what can we do with that? Now so we have these two constraints, equation 4 and equation 3. Now these constraints put restrictions on the value of the energy E that you can have. Right? Done this kind of thing before. These constraints on your wave function, on your U, your single valued, normalizable, blah blah blah, all those conditions, they force to a large extent they in a sense force the discretization, the quantization of the energy, right? So what we need to do now, so we've got these two equations we can solve. Let's concentrate on. We'll just do one example here. We'll do equation 4, which is this one. Now, start thinking about this a little. You've got two values. You've got this cot alpha a on the left side, and you've got minus beta over alpha on the right hand side. Now, both of these two values, both of them depend on the energy. Right? So, well, A is a constant. That's just the size of your region. That's just a constant. That's a given, right? So that doesn't vary. But alpha, what's alpha? Alpha's here. Alpha's square root of 2me. Now alpha, so h bar is a constant, m is a constant, but e can change. E is a variable. It can vary. It's a variable. Okay. So that means alpha is a variable, right? So alpha depends on E. Alpha is a function of the energy. Alpha is a function of E. And now V naught is a constant, H bar is a constant, M is a constant, but E can vary. E is a variable. So beta here, also a variable. Beta is a function of the energy. Okay, so alpha and beta are both variables of the energy. Okay, now here you've got an alpha here. So you could draw a graph of this where, let's see, you could have your energy along the horizontal axis and this value is, say, the vertical axis, and for differing values of E you could draw two graphs. You could draw